Welcome back. This is Mr. Boothman. We're talking about section 7.5 today, which is polar or trigonometric forms of complex numbers. This section and the last section of this unit are fairly different compared to what we've just studied and the rest of the trig that we've studied. But I think they're also a really interesting concept in math that we don't really get to talk about otherwise in high school math. Um, so we're going to start by talking about a different way of graphing coordinates or graphs in the coordinate plane. Now, up until now, we've only ever looked at the rectangular coordinate system. So we have our rectangular coordinates, we have a two-dimensional plane, and we use an x value and a y value, a horizontal value and then a vertical value, to tell someone the position in our coordinate system on that plane. But of course, there are so many other ways we could describe your position in that two-dimensional plane. And one of the other most commonly used ways of describing that is what we call polar coordinates. So polar coordinates take, that's what this graph is here. Polar coordinates are described also using just two values. One is the angle from standard position, and the second is the distance from the origin to where you are. So this point P right here, we can describe where that is with an x value and a y value, horizontal and vertical. We could also describe this using how far it is from the origin, this r value right here, and then the angle that it makes, the angle that makes from standard position. Using just those two pieces of information, I can figure out where I am in this coordinate system. And you might be asking, well, we've only ever used x and y coordinates, why are we studying a different kind? And really, polar coordinates are used a lot in especially higher math because they're a lot more convenient for certain types of graphs. If you think about a circle, or you think about what a function means in the rectangular coordinate system, like a circle isn't a function, right? Because it fails the vertical line test. We don't have to worry about that in polar coordinates. And so that's one of the main reasons that people use polar coordinates. And we're going to see that it also ties really deeply with complex numbers, which we've talked about in the past. So bear with me. The section's just new, I think. It's going to be kind of different. But let's take a look at how we can convert between these two coordinate systems first. So starting here, you have some handy formulas here, but I want to go through what that means. So if I'm given polar coordinates, if I'm given this point P right here, and I'm given r, which is the distance from the origin, and theta, which is the angle from standard position, how could I convert that to an x value right here and a y value? So I want to find this x and this y. Well, notice this is just a right triangle. The cosine of this angle here is adjacent over hypotenuse, which is r. This was our distance from the origin given to us here in the polar coordinates. So if I solve that for x, I get x equals r times the cosine of theta. Similarly, sine of theta is opposite over hypotenuse, so y is r times the sine of theta. So that's where these first two formulas are coming from. So if I want to convert from polar to rectangular coordinates, so I need to find x and y, I just have to use these two formulas. And it's fairly similar to everything that we've been looking at when we study triangles in the rectangular coordinate plane. If I want to change from rectangular to polar coordinates, well, then I'm given x and I'm given y. I need to find r. So that's just the Pythagorean theorem. And then I need to find this angle here. So if I know x and y, opposite and adjacent, then I'm looking at tangent of that angle is opposite over adjacent. And so I could use the inverse tangent function to solve for the angle. So that's where I'm getting this formula right there. So that's where these formulas are coming from. Let's go through a couple of examples of converting between these two kinds of coordinates. So let's take 4 and 2 pi over 3, and we're told that's in polar coordinates, so that's r, the distance from the origin, and theta, the angle that that makes from standard position. And we want to convert that from polar to rectangular coordinates. So I want x and y. I want to change this to some x, y point. Well, x is r times the cosine of theta. And I'm given those values. R is 4, and then theta is 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2. So this is negative 2. And y is r times the sine of theta. So 4 times the sine of 2 pi over 3. And that's 4 times, sine of 2 pi over 3 is the square root of 3 over 2. Or 2 times the square root of 3 if I simplify that. So x, y, my rectangular coordinates are negative 2 and 2 square root of 3. So if I plot that point, just like we're familiar with from our years of algebra, our years of math, that is going to be the exact same point as if I took this point in polar coordinates and found that angle, 2 pi over 3, and then went 4 distance from the origin. Okay, I know it's a strange way to think about these graphs, but trust me, it really does make it easier for certain graphs, and especially it makes it easier when we talk about complex numbers. So moving on, I'm going to go ahead and go through example 2 with you as well. So convert 2 and negative 2 from rectangular to polar coordinates. So now this is rectangular coordinates, that's x, y, and I want to change this to polar, which is in the form r theta. Well, r squared is x squared plus y squared. So r squared equals 2 squared plus negative 2 squared, which is 8. So if I take the square root of both sides, r is the square root of 8, which you could simplify to 2 times the square root of 2 if you're really comfortable with that. Note that I don't get a negative. Even though I took the square root, r is distance, so r has to be positive. And then how do I find theta? Well, if we look at this triangle, we look at the formula, we see that tangent of theta is y over x. So y over x is negative 2 over 2, which simplifies to negative 1. So you can take your calculator and do theta. It's going to equal the inverse tangent of negative 1. Or hopefully you're comfortable enough, especially after 7.3 where we studied solving trig equations, hopefully you're comfortable enough with saying, all right, tangent equals negative 1 at what angle? Well, tangent is negative in the second and fourth quadrants, and I know that the range of the inverse tangent function, or the range, yes, the range has to be in the first or the fourth quadrant. So I'm looking at the fourth quadrant. And where is tangent? Y over x equal to negative 1. That's going to be 7 pi over 4. Or your calculator will give you an answer of negative 45 degrees or negative pi over 4. They're the same angle. They're coterminal. So that's a lot of reasoning, but this is also why we do this after we've developed our knowledge of the unit circle and understanding the inverse trig functions and understanding how to solve those equations. So theta is 7 pi over 4. So that means my polar coordinates, r theta, are 2 square root of 2 and 7 pi over 4. Those are my polar coordinates. So if I plot that point, it's going to be the same as if I plotted xy equals 2, negative 2. Okay. So let's look at converting a whole equation to polar coordinates. And these are kind of fun because we're really just substituting. So convert the equation x squared equals 4y to polar coordinates. So x squared equals 4y, so that's a quadratic equation. We want to convert this to polar coordinates, and so we're going to use those same formulas up here. X equals r cosine theta. So instead of x here, I'm going to write r cosine of theta squared equals 4 times y is r sine theta. All right? And now I just simplify. I try to solve for r. So r squared times cosine squared equals 4 times r times sine of theta. Okay, divide both sides by r, so an r is going to cancel out. And then I'm going to divide both sides by cosine squared, so I get 4 equal, or r equals 4 times sine of theta over cosine squared theta. Sine over cosine is tangent. And then 1 over cosine is secant. So r equals, my final converted equation is r equals 4 times tangent theta secant theta. And so if I were to plug in different values for theta into that equation, I would be graphing the exact same thing as if I graphed x squared equals 4y, the way we've always done graphing. I think this is a really interesting way of thinking about these graphs, particularly about thinking of curves and circles and all kinds of interesting shapes. Unfortunately, we don't have too much time to actually go into the really weird-looking graphs that we can do with polar coordinates, but I do encourage you to come talk to me if that interests you, and to definitely check that out on your own if you'd like. So I'm going to see if you can try example 4 on your own. So here I'm converting from polar to rectangular. Okay, now that means I'm using these formulas here. We're actually going to end up using both. And these can be a little tricky. There's kind of a trick to them. If you can't figure them out on your own, come talk to me, and we'll definitely go over them in class, okay? So that was just basic converting between the two. That is a learning target this section, so I expect that you can convert. So this would be a great time to pause. I'm warning you, this is going to be kind of a long video, so we're 12 minutes in right now. Go ahead and pause if this is the only section you needed. Otherwise, we are going to jump in to talking about complex numbers, which I know seems unrelated right now, but we'll see why that's being introduced here. So we talked about complex numbers last semester, and you've talked about complex numbers in math classes before that. So you should understand what I is. I equals the square root of -1. This interesting concept that we've defined in mathematics. But we've never really talked about graphing complex numbers. At least I don't believe that you have. If you have, that's great. This is a bit of a review. But it turns out that every complex number corresponds to a particular point in what we call the complex plane. And so I think graphing complex numbers is super easy because as long as you can count, you can do this. So in the complex plane, it's this picture right here. We define one axis to be the real axis, the real part of the complex number. And then we define another part of the plane to be the imaginary axis, the imaginary part of the complex number. So if you need a quick refresher, let's say I have a complex number. We'll call it z. And that's always in the form of a plus b times I. So a and b are real numbers. But a here is the real part of this number, and then b times I is the imaginary part. It's because it has the imaginary number with it, the I. So how do we plot these? Well, let's look at letter A. 4 plus 3i. 4 is the real part, so I'm going to count 1, 2, 3, 4 along the real axis, and then go up 3, 3i, the imaginary axis. That's my point. That's where A goes. So for B, -5 along the real axis, 1, 2, 3, 4, 5, and then down 4 along the imaginary axis, 1, 2, 3, 4. That's letter B. C, there's no real part of this imaginary number, or this complex number. There's just negative 4i, so I'm going to count 1, 2, 3, 4 down the imaginary axis. That's letter C. B is 2, 1, 2, minus 3i, 1, 2, 3. And then E is 3 minus I, so 3 along the real axis, minus I along the imaginary axis. Pretty straightforward, hopefully. So plotting complex numbers is pretty straightforward, I think. Now, if we think about the absolute value of a complex number, the absolute value of any number, even in the real number system, is defined as a distance, right? Absolute value is always positive because it's the distance from the origin. If we're talking about the absolute value of negative 10, that answer is 10. It's 10 away from the origin of 0. So for these complex numbers in this two-dimensional plane, the absolute value is going to be the distance from the origin, from 0, 0, right here in the complex plane. So the absolute value of a complex number, z equals a plus bi, is defined as the absolute value of c. We still use the same absolute value bars. Equals, well, let's consider a right here. So I want to know what this distance is. That's going to be the absolute value, the distance from 0, the origin. Well, here's our triangle. This leg right here is the real part. Okay, that's the A part from this number. And this part right here going up was B. That was this part of a complex number, the imaginary part of the complex number. So if I want the distance, the hypotenuse, how do I find that? A squared plus B squared, and then take the square root. So the absolute value of any complex number is defined as the square root of A squared plus B squared. Now, hopefully that makes intuitive sense to you. And if not, go back and listen to that explanation again. And we're definitely going to talk about this in class also. But really, that's the distance of z, that complex number, from the origin in the complex plane. And why is that? Because in all the other kinds of numbers that we talk about, absolute value is distance. That's why it's always positive. Okay? So it has to be the same here. It has to make sense with everything else that we do in math. So let's look at some examples. I want the absolute value of this number, 6 minus 8i. Well, this is a plus bi. That's always our standard form of the complex number. And so the absolute value of that number we just defined as the square root of a squared plus b squared. Well, in this complex number, a is 6, and b, and this is the trick here, is negative 8. Because standard form is a plus bi. So that means if we have minus a number there, b is negative. So the absolute value of this particular complex number is the square root of 6 squared plus negative 8 squared. That's the square root of 36 plus 64, or the square root of 100, which is 10. And again, it's positive because absolute value is positive by definition. Now, think about what that's saying. Okay, I used an example just a few minutes ago that the absolute value of negative 10 is 10. It's 10 away from 0 on the number line. I'm also telling you right now that the absolute value of the complex number 6 minus 8i is 10. That's so fascinating. And I'm sure you're sick of me getting so excited about these things in math, but the fact that all of this makes sense and it relates to one another is just extraordinary to me. And I do hope that some of you are starting to feel the same. Now, let's take a look. I'll let you try letter B on your own. Okay. So that's finding the absolute value of a complex number. And we're about to see why we just went through that. So again, we're at 20 minutes into this video. This is going to be long. I apologize. But let's move on, and you might be able to guess where I'm going with this. Just looking at the complex plane here, how we define complex numbers. We drew this triangle to find the absolute value. But what did we start this section with? We were talking about a different way of defining coordinates, polar coordinates. We can do the same thing with these complex numbers. I can define this letter A right here, 4 plus 3i, in polar coordinates. And there's tons of reasons why we do that and why it makes other things in math so much easier. And I'd love to talk to you about that, but I don't want to make this a 3-hour-long video. So let's talk about what the polar form of a complex number will look like. Now, note, polar form of a complex number is also going to be called the trigonometric form of a complex number, and we're going to see why. But those are interchangeable. Those are the same. Those mean the same thing. So if I have a regular complex number, z equals a plus bi, that's called standard form. The polar form of this number, well, what is a here? What was a here? Polar, I need this distance, r, and I need this angle, theta. So a, well, that's going to relate to the cosine of this angle, adjacent over hypotenuse. So if I want to solve for that a value, a is r times the cosine of theta. And similarly, b will relate to sine, opposite over hypotenuse. So b is r times the sine of theta. That's where we get that. R is the square root of a squared plus b squared, right? This is the hypotenuse of this right triangle, but we also found that r equals the square root of a squared plus b squared. That's just the absolute value of the complex number. That's also why we just talked about that. So if we put this all together, r times, well, let me take a step back for a second. Z equals a plus bi. We just said a was r cosine theta, and we just said b was r sine theta times I. I can factor out an r from both numbers, and then I'm left with cosine of theta plus I times sine of theta. And that itself, that right there, is the polar form of a complex number. We call it the trigonometric form of a complex number as well because we're dealing with cosine and sine of an angle. And we just defined all of this right here. And then tangent of the angle equals b over a, for the same reason as before. If we look at this angle in here, tangent of that theta is opposite over adjacent. The number r, that was the absolute value of this complex number. We also have a really special word for it in math. That we call the modulus of the complex number. And then theta is called an argument of the complex number. Argument is what we plug into a function usually. We use that especially when we're talking about logarithms. The argument of the log is what we're plugging into, is what's inside the log. So that's similar reasoning here. And then the modulus, just know that it's a fancy word that we use and be able to recognize what it means. So the modulus is the absolute value here. So let's look at some examples of this, because your second learning target for this section is to convert complex numbers between these two forms, standard form, a plus bi, and polar, also known as trig form, z equals r times cosine theta plus I sine theta. So we're given this complex number that's in standard form. That means this is a plus bi. So right away, I'm going to identify what does a equal. A is -2, and b is negative 2 square root of 3. And I want to write this in trig form, or polar form. And so to write it in polar or trig form, I need r and I need theta. So let's solve for theta first. And I'm going to use tangent of theta. I know b and a, so tangent of theta equals b over a, which is negative 2 square root of 3 over negative 2. Simplify that, it becomes square root of 3. Now hopefully from 7.3 you recognize that the denominator is 1. Unsimplify this, becomes square root of 3 over 2 over 1/2. That's y over x. So where does theta equal that? That's going to be either pi over 3 or 4 pi over 3. But I can't have two different angles here. So the trick here, there's always a little trick, I'm sorry. The trick here is to look at the number we were given, negative 2 and negative 2 square root of 3. What quadrant is that in? If I were to graph this complex number, where would it go? Negative 2 is the real part, then minus 2 square root of 3i, that's somewhere down here, right? So that's in the third quadrant, and in the third quadrant is that pi over 3 or 4 pi over 3? The answer is 4 pi over 3. So that is my theta. So we have to think about where this complex number actually exists in the complex plane and then eliminate the other angle that we would get when we solve this equation. I know that's a lot. Pause if you need to and process that. Think about what I'm saying. Listen to what I just said again if you need to. So that's theta. I also need to find r. R equals square root of a squared plus b squared. So that's the square root of negative 2 squared plus negative 2 times the square root of 3 squared. Square root of 16, which is 4. So now I have all the pieces I need to write this complex number in trig form. Z equals r times the cosine of theta plus I times the sine of theta. Now, you could leave it like this. We could find cosine and sine of 4 pi over 3 and then simplify all of that. But for now, I just want you to understand how we get it into this form to begin with. So go on ahead and try example 8 yourself. And now careful, because here you'll find that theta is not just a nice angle on the unit circle, so you will need to use your calculator. Little warning there. And I will go through example 9, and then we'll dive into the very last topic for this section. And I know we're at almost 30 minutes right now. I am trying, I'm sorry, but this is a huge section, and I want to make sure that we devote the proper time to it. So example 9, we have a complex number given to us in trig form, and we want to convert it to standard form. Remember, trig and polar form mean the same thing. And we want to change it to standard form, which is z equals a plus bi. I need to find b, and I need to find a. I was given r and theta. So let's use our formulas. I need a and b, so that's this formula and this formula. A equals r cosine theta, r times the cosine of theta. Cosine of negative pi over 3, that's the cosine of 5 pi over 3, which is 1/2. And if we simplify that radical, we get 2 square root of 2 times 1/2, so a is square root of 2. If you're not comfortable simplifying radicals, come talk to me. B, using our other formula, is r times the sine of theta, square root of 8, times the sine of negative pi over 3. Sine of negative pi over 3 is square root of 3 over 2. Okay, now we said square root of 8 is 2 times the square root of 2. 2's cancel. I can multiply those radicals together. And actually, sine of negative pi over 3, that's going to be negative square root of 3 over 2. Sorry about that. So I get negative square root of 6. So this is A, this is B, so I can write this form. Z equals A plus B I. And that's the complex number. It's the same as if I graphed this in the complex plane, where r is the distance from the origin, and theta is the angle in standard position. That was a big topic, and this is so different from so much of what we've ever done in math, or what you've ever done in math. So please don't be worried about understanding everything I just said. It's a lot, and I know it's a lot. We're going to spend plenty of time on this. I want you to be comfortable. So rewatch this as much as you need to. Pause it for a second before we go on to the last part of this section. There's one last thing that we need to talk about. And kind of part of the reason why we bother writing complex numbers in polar or trig form, and that's multiplying and dividing complex numbers in polar and trig form. Multiplying and dividing complex numbers can be complex, if you'll pardon the pun. It's not always very fun, but in polar or trig form, it's actually pretty straightforward. We can talk about where these formulas come from another time. If you want to, come talk to me. But you're not given these formulas on a reference sheet. You will need to remember this, but they are straightforward. If I'm multiplying two complex numbers in polar or trig form, then that product, z1 times z2, is just the product of the r's times cosine of, I add the angles together, plus I times the sine of adding the angles together. So if I have two complex numbers, z1 and z2, z1 has r1 and theta 1, and then z2 is r2 and then theta 2. Then if I multiply them together, that product is just multiplying the r's together times cosine of, add the angles together, plus I times the sine of adding the angles together. So let's do example 11, and then we'll look at dividing. So example 11, find the product of these two complex numbers. So this is z1, that means this is r1 and theta 1. This is z2, so 8 is r2. This is theta 2. So using our formula, z1 times z2 is r1, r2, times the cosine, theta 1 plus theta 2, plus I times the sine of theta 1 plus theta 2. R1 is 2, R2 is 8. Cosine of theta 1 is 2 pi over 3. Theta 2 is 11 pi over 6. And that's going to be the same inside sine here. And now it's simplification. Okay, so 2 times 8 is 16 on the outside times cosine of, I need a common denominator, that's going to be 6. So 4 pi over 6, what's 2 pi over 3, plus 11 pi over 6. And 4 pi over 6 plus 11 pi over 6 is 15 pi over 6. And 15 pi over 6, let's find a coterminal angle that actually makes sense to us. So 15 pi over 6, subtract 2 pi from that. That means I'm subtracting 12 pi over 6 for 3 pi over 6, which reduces to pi over 2. So the angle there is actually cosine of pi over 2 plus I times the sine of pi over 2. And cosine of pi over 2 is 0. And the sine of pi over 2 is 1. So 0 plus I times 1, that's just I. So 16I. And so hopefully you see why we cared about polar form here. Multiplying these two numbers together is 16I. That's the product. And I don't know about you, but I would have hated doing that using box method for two really complicated, complex numbers. Having polar or trig form makes that so much simpler. And so it's the same for the quotient, for dividing two complex numbers. The quotient there, we're dividing the two r's and then subtracting the two angles. So looking at an example of that, here is z1 and z2, so that means this is r1, this is theta 1, this is r2 and theta 2. z1 over z2, because I want the quotient, is going to be r1 over r2 times, I can't say r2 without thinking of Star Wars, I'm so sorry, times the cosine of theta 1 minus theta 2. So this is just the formula. Again, you will need to know this formula. It is not on your formula sheet, but don't worry too much. I think it's pretty straightforward. If I'm multiplying r's and adding the angles. If I'm dividing the r's and subtracting the angles. So simplify this, or plug in our numbers. R1 is 24, R2 is 8. We have cosine of theta 1 is 300 degrees. So notice we have degrees instead of radians this time. Minus theta 2 is 75 degrees. And I'm running out of room. Plus I times the sine of the same. And now we simplify. 24 divided by 8 is 3. Times the cosine of 300 minus 75 degrees is 225 degrees. Plus I times the sine of 225 degrees. Cosine and sine of 225 degrees, so let's see, that is in quadrant 3, which means they are both negative. Negative square root of 2 over 2 minus square root of 2 over 2 times I. Multiply by 3. Negative, and that is the quotient. What I would get if I divided these two complex, or when I divide these two complex numbers. Oh, boy, that was a section if I've ever seen one. So that was a lot. And I know that was a lot, but we will spend plenty of time in class on this. And I encourage you to go back through and rewatch parts of this that confused you. Come to me with questions. Do practice. I say the same things in every video, but that's because I need you to be doing these things. Okay. So thank you so much for watching. I know this was long. Have a wonderful day, and we'll see you in section 7.6.